All right. Hi, everyone. Our topic is to find the dominant and non-dominant factors for insurance costs and number of quotes using the Bayesian statistic. Our group member is Ben, Carlos Wong, Sean Yan, and Melanie Koo. There are two questions we want to ask. The first is commonly said that homeowner status, marital status, and age of vehicle are dominant factors in determining insurance costs. Can we find the pattern in our data? Another question is that logically to think that the more expensive insurance, the more number of calls customers options before purchasing insurance. Is that true with our data? So here is the data description. We get 1,000 out of 97 unique customers from the All States Cargo Challenge. Our extracted data consists following variables. Customer ID is meaningless. There are two target features, the cost and the shopping point. The cost is the insurance cost. The shopping point is the number of insurance costs before the customer made the final decision. There are four explainable features: group size, homeowner, car age, and married couple. Group size is either 1, 2, 3, 4. Homeowner is yes or no. Married couple is also yes or no. The car age is the age of car range from 0 to 20. And then we will show you the demographic of customers. So here we have four features. The first one is the marital status. We can find only a quarter of them is married. And the homeownership status is about half and half. The group size have most of them 800 out of 1,000 of them have a group size of 1. And we can find the final is the car age. The count decreasing as the car age increasing. Next, we'll find the correlation between the cost and those explainable features. We can find in the first row the car age, homeowner, and married couple has a highly correlated with the cost, and group size we can find in the right graph is close to 0. So we will basically build two models. The first model includes homeowner, car age, and married couple, and the second model only use the car age to build the model. Then I will show you how we build the model. We can find the distribution of customers' insurance costs is a normal distribution with a mean of 615 and a standard deviation of 200. So we will build our model based on the fact that it's normal distributed. We welcome Melanie to tell how we build the model.
Thank you, Sean. So we'll build the first model for the first question, which asks which of the explanatory variables are most explanatory of the cost of insurance. So we built a first Bayesian regression model using all the betas and all the only 3 of the variables: the homeowner, the married couple, and the age. So we have 2 parameters, alpha and sigma squared, and we use the linear combination of the betas and along with the variables to get alphas of I, and then we used a flat prior for the betas of intercept for all the betas, and we used a flat prior for the sigma squared, a relatively flat prior. Next, we initialized the model by using 4 chains and using very extreme values for all the betas and the sigma squared of inverse. So next we run the convergence test for the novel number 1. So we have the Gilman-Rubin diagnostic, which is less than 1.1, which means that all of that the model that there's no convergence issues with the model. And then we ran the effective sizes of the model, and we checked for the plots, and they all seem to converge. Next, we ran the 95% confidence interval check for the beta. So we have so we determined that if the 95% confidence interval of beta does not include 0, that means it's statistically significant. So found that to be true, and also we found that the means of the betas also fall within the region, the confidence region. Next, we have the second model for our first question, which is another Bayesian regression model. So in this model, we only use the car age as the explanatory variable. So we have a normally distributed, identically and normally distributed normal variable with alpha and sigma squared as the parameters. And we have the alpha and the linear combination again of the betas and the car age, and we have a relatively flat priors. So we initialized the model again using 4 chains and very extreme values, as you can see for the betas. And then we ran the JAX model, and then we updated it for 10,000 burn-ins. Next. And then we ran the convergence test for model number 2. We found that the Gilman diagnostics are all less than 1.1, effective sizes are all greater than 400, and the Gilman plots seem good. So next we have the 95% confidence interval checks for the betas. So we notice that the 95% intervals of the betas do not contain 0. So that means that this model is statistically significant. And also the means of the betas also fall within the confidence interval. Next. So then we have a comparison of the models number 1, number 2 based on the DIC. So we noticed that the DIC values for the model number 1 and number 2 are around the same. And car age is probably a more dominant factor than ownership status and marital status because the latter 2 models only improve the penalized deviance by about 0.6%. Next, you have Han introduce the last model.
Thank you, Melanie. And for the second question, which is to build to see if the cost of insurance directly cost members to obtain more number of quotes before before making a purchase decision. And specifically here, we're building a Poisson log linear model where the number of quotes people get is the target variable and the cost of insurance is the explanatory variable. And we are assuming this follows the Poisson distribution. And the log of Poisson is an offset factor plus an intercept plus a beta multiplied by the cost of insurance. And you'll notice that the offset factor here is log of 1. Ideally, we would like to have the offset factor to be the amount of time people spend pulling up, requesting quotes. However, we don't have that piece of data available. The closest proxy we have is the number of insurance policies these customers purchase. And the data we're given said that all the customers only purchase 1 policy. Therefore, the offset factor here is log of 1, which is the same as 0. For the betas, we assume that they are normally distributed and they're really flat prior because we don't know much about the distribution of the betas. We set up 4 chains and with extreme values and ran a JAX model. After running the model, we did a convergence test in the looking at the Gell-Mann-Rubin diagnostics as well as the plots. There are no convergence issues. The effective sample size are greater than 400, so that is good. For the 95% confidence interval, the confidence interval for beta intercept spans from 6.6 to 6.93, and because the value 1 is not included for this log linear model, therefore we can say that the beta intercept is statistically significant. However, for beta cost, the value 1 is within the 95% confidence interval, so we cannot make the same conclusion. And this is something that we will address in subsequent slides. For the chi-square test, and the test statistics come back at 1. So that means that we have a under-dispersion issue, meaning that the variance that our model assumes is larger than what the data suggests. And this is possibly could be resolved if we had better offset factor, but given that we don't have the time people spend on obtaining their quotes, there's nothing really we can do about this. So for completeness sake, we ran a DIC on this model, and the table on the left is about that. The conclusion for our question 2 is that given beta cost 95% confidence interval in the chi-square test, the number of quotes that customer obtain does not really depend on the cost of insurance. And are there any factors that we could model to estimate the number of quotes the customers get? Perhaps, but given the limited amount of data we have, that we cannot really do that in this case. So this concludes our presentation. We thank you for your time for listening to our presentation. Thank you.